Have you ever wondered about the limit of our computing power? As we delve into the digital age, we're constantly pushing the boundaries of what's possible with our technology. But there's a snag. Our classical computers, as advanced as they are, have limitations. They operate on bits, binary digits that can be either 0 or 1. But what if we could go beyond that binary? Enter quantum computing, a realm where bits transform into quantum bits or qubits. These qubits, unlike classical bits, can exist in multiple states at once. Imagine being able to process vast amounts of data simultaneously or solve complex problems in a fraction of the time it would take the most powerful supercomputers today. This is the potential of quantum computing, a field that promises to revolutionize everything from cryptography to climate modeling. So the question arises, how far have we come in the field of quantum computing? The journey of quantum computing begins in 1980. It was a time when the computer industry was booming, and the race to create faster, more powerful machines was on. Amid this technological frenzy, a physicist named Paul Benioff was thinking outside the box. He introduced a new concept that would change the landscape of computing forever: the first quantum mechanical model of a computer. While traditional computers operated on bits, ones and zeros, Benioff proposed a system that operated on quantum bits, or qubits. These qubits, he theorized, could exist in multiple states at once, thanks to a little-known quantum phenomenon called superposition. This meant that quantum computers could potentially process vast amounts of data simultaneously, a feat impossible for classical computers. The 1980s and 1990s were decades of exploration and experimentation in quantum computing. Scientists were intrigued by Benioff's radical idea, but turning theory into reality was no easy task. The principles of quantum physics are notoriously difficult to understand and even harder to manipulate. However, the potential of quantum computing was too great to ignore. Enter Richard Feynman, a physicist known for his work in quantum mechanics. Feynman was a big believer in Benioff's quantum computing concept. He argued that a quantum computer could simulate the universe in a way no classical computer ever could. Feynman's endorsement of quantum computing was a significant push for the field, spurring further research and development. By the late 1990s, the first rudimentary quantum computers were being built. These machines were far from perfect, but they were proof that quantum computing was more than just a theory. They marked the beginning of a new era in computing, an era where the rules of quantum physics could be used to solve complex problems at unprecedented speeds. The birth of quantum computing was a historic moment in science and technology. It was the merging of two seemingly incompatible fields: the concrete binary world of computing and the elusive probabilistic world of quantum physics. From there, quantum computing started to take its shape. As we entered the 21st century, quantum computing began to heat up. The early 2000s were a period of significant progress, with the creation of the first quantum bits, or qubits, being a significant milestone. These qubits, unlike classical bits, can be both 0 and 1 at the same time, thanks to a principle known as superposition. This is where the magic happens, as it allows quantum computers to process a vast number of possible outcomes simultaneously. But what good is a quantum bit without a quantum computer to put it to work? Enter D-Wave Systems, a Canadian quantum computing company. In 2009, they made headlines by developing the first ever commercial quantum computer. This was a game changer, heralding a new era in computing technology. This machine, named D-Wave 1, was an absolute marvel. It boasted a whopping 128-qubit processor, a remarkable feat for the time. This breakthrough by D-Wave Systems was the spark that ignited the quantum computing revolution. It was the proof of concept that the world needed, showing that quantum computing was not just a theoretical possibility, but a practical reality. This was a pivotal moment in the history of computing, marking the transition from the realm of the theoretical to the tangible. Since then, the field of quantum computing has only accelerated. Developments have been coming in thick and fast, with more and more companies and research institutions throwing their hat into the quantum ring. Each new breakthrough is pushing the boundaries of what is possible, leading us into a future where quantum computing could become a part of our everyday lives. So as we look back at the early 21st century, we can see it as a time of intense growth and innovation in the field of quantum computing. It was a period that laid the groundwork for the quantum revolution that we are witnessing today. But as they say, this was just the beginning. The quantum computing revolution was just getting started. The past decade has seen some of the most significant breakthroughs in quantum computing. The years between 2010 and 2019 were indeed a thrilling ride in the world of quantum science. Let's cast our minds back to the year 2019, a landmark year in the quantum computing timeline. It was the year when Google, one of the tech giants, claimed quantum supremacy. This was a bold assertion that they had built a quantum computer capable of performing a calculation that would be practically impossible for a classical computer to execute. This was a momentous occasion, a real game changer, marking a significant leap in our journey towards the quantum future. But the quantum leap wasn't just about quantum supremacy. It was a decade that also saw the development of quantum algorithms. These algorithms, built specifically to exploit the quirks of quantum physics, have the potential to solve problems in a fraction of the time it would take classical computers. They have been used in everything from cryptography to the modeling of complex molecular structures, and then there's the progress in error correction techniques. Quantum computers are notoriously delicate, with their quantum states easily disturbed by environmental factors. But scientists have been developing methods to detect and correct these errors, bringing us closer to the dream of stable, reliable quantum computing. So, it wasn't just about faster calculations, it was about building a whole new way of computing, of understanding, and of solving problems. It was about pushing the boundaries of what we thought was possible. These developments have brought us to the brink of a new era in computing, an era where quantum computers could become a part of our everyday lives, changing the way we approach problems and opening up a world of possibilities. The quantum leap of the last decade has set the stage for the exciting developments that lie ahead. And with each new breakthrough, we get one step closer to that quantum future. With such rapid advancements, what does the future hold for quantum computing? Quantum computing, in its future form, promises to revolutionize our world in profound ways. The potential applications are vast and span across numerous industries. Take cryptography, for instance. Classical computers can take thousands of years to crack complex encryption techniques. However, a fully realized quantum computer could potentially do this in a matter of seconds. This has significant implications for data security, which is becoming increasingly important in our digital age. In the realm of drug discovery, quantum computing could be a game changer. The process of discovering new drugs involves simulating and analyzing complex biological systems, which can be incredibly time-consuming and resource-intensive. Quantum computers, with their ability to process and analyze large amounts of data at unprecedented speeds, could dramatically speed up this process, potentially saving millions of lives. And let's not forget about climate modeling. Our current models are good, but they're not perfect. Quantum computers could help improve these models by processing vast amounts of climate data more efficiently, potentially providing us with more accurate predictions and allowing us to respond more effectively to climate change. Yet, despite its immense potential, quantum computing still faces significant challenges. One of the biggest is qubit stability. Qubits, the basic units of quantum information, are extremely sensitive to their environment. Even the slightest disturbance can cause a qubit to lose its quantum state, a phenomenon known as decoherence. This makes building a stable, reliable quantum computer incredibly difficult. Another major challenge is the need for extremely low temperatures. Quantum computers need to operate at temperatures close to absolute zero to minimize thermal noise. This makes them difficult and expensive to build and maintain. Nevertheless, the future of quantum computing looks bright. With ongoing research and development, we're slowly but surely overcoming these challenges and inching closer to realizing the full potential of this revolutionary technology. The quantum future might not be here just yet, but it's certainly on the horizon. The future of quantum computing looks promising, but the journey is far from over. So, how does all this put into perspective the importance of quantum computing? Well, let's take a moment to reflect. We've journeyed from the birth of quantum computing through its evolution in the 21st century and taken a leap into its future. And what a future it is! Quantum computing holds the promise of revolutionizing sectors from healthcare to finance, from climate science to artificial intelligence. By harnessing the power of quantum mechanics, these supercomputers can process information at speeds unimaginable to classical computers, allowing us to solve complex problems and even simulate the mysteries of our universe. We are standing on the precipice of a new era, an era where quantum computing is no longer a distant dream, but a tangible reality. The journey may be complex, fraught with challenges and unknowns, but the potential, it's limitless. Quantum computing might be complex, but its potential is limitless. It's a journey worth watching, wouldn't you agree?